Hi everybody, Ali from Pullin here. It's time for the mystery to end. So in parts 1 and 2 of this series, I was trying to give people an opportunity to guess what Arduino-based robot I was building and the movie which inspired me. So without further ado, the movie that inspired me was Minority Report from 2002. When I was trying to figure out what kind of robot I wanted to build, I remember the scenes from that movie where spider-like robots were hunting Tom Cruise.
So these robots go under a locked door to find him, and I thought to myself, I wonder if I can build a robot that can actually go under a door. So I immediately went to Google to see if someone had already done it. I searched for robot under door and came across a robot called Star. This is an amazing robot designed in 2013 by some researchers at UC Berkeley. As soon as I saw this, I said, I have to build that. So that's what I've been doing, recreating the Star robot using 3D printed parts in an Arduino-based electronic control system. I want to use commercially available parts so others can try to build this super fun robot if they want to. Now let's take a look at the CAD and talk about how Star works. So here we have the CAD layout I have created for the Star robot. As you just saw, Star stands for Sprawl-Tuned Autonomous Robot. What the original designers mean by sprawl is that the robot can adjust its height by means of these two hinged pieces on the side. When the center motor turns, it drives these two gears, which in turn drive two belts to these outer pulleys. Those outer pulleys are coupled to the side hinge pieces, and that allows the height to be changed. The reason we use gears and not just belts on the two sides is that each side has to rotate in an opposite direction in order for the robot to change its height. These gears provide the means to reverse the direction of rotation from one side to the other. This sprawl feature is really innovative and is what allows the robot to flatten itself to go under a door. The other two motors each drive the hybrid wheel/legs, also called WEGs, on each side of the robot. They use the bevel to spur gear arrangement that I showed in the part 2 video. Now that we've seen the CAD, let's take a look at the real life parts. These are the final mechanical components of the robot. We have the subassemblies from part 2, which we tie together on the main body. The front portion, which changes the sprawl of the robot, is the same as was shown in part 2. The final electronics will mount on the main body. You can see that I make use of heat set inserts, which is crucial when working with all these really small plastic parts. Let's take a closer look at the side pieces. We have the bevel to spur gear arrangement that was shown in CAD. On the bottom, we have the 3 WEGs attached to 3 of the spur gears. The other gears have simple caps that retain them in place. The side pieces couple to the main body through these dowel pins and set screws. And that's what forms the hinge that allows the side pieces to rotate. The front dowel pin also has a pulley attached to it, and that's what allows the sprawl mechanism to drive that rotation. Okay, so here are all the mechanics assembled together. I don't have the final electronics done yet, but let's drive this guy around using a tether. Before I close out this video, I want to say a little bit more about the original designers from 2013. This robot design comes out of the Biomimetic Millisystems Lab, that's a mouthful, at UC Berkeley. I'll put links to the original paper, video, and lab website in the description of this video. If you think this robot is as awesome as I do, please go and give them some love through these links.
Alright, the building of the robot is almost complete. Next will come the super fun part of testing it out. which I'll do in the next video. Do you think it can actually fit under a door? Be sure to subscribe so you'll see that video as soon as it releases. I'll see you guys next time. Now go print something potent.